In the name of Almighty God, I am Master Hassan Koshi, and today I want to talk about prescribing condition on fluid-solid interfaces. Defining condition on interfaces between different phases typically involved in the contact with a fluid. It is worthwhile to be careful with how variables in the conditions are evaluated. Consumer physics supports that variables are defined differently on agents and domains or any other geometry dimension. Evaluating a variable with differing definitions that mean value is written on a boundary separating the different domains. The density, pressure, or temperature are examples of variables that may differ in a fluid and a solid. In order to specify on which side a variable is evaluated, the up and down operators described in the Council Physics Reference Manual can be used. Now I want to go through the species properties. Use this node to define parameters specified to each of the species. The node will change its label depending on what inputs are available in the node. If only molar mass is available, it will be labeled as species molar masses. Now I want to go through the molar mass integral value expression for the molar mass MW for each species. The default value is 0.032 kilogram per mole, and which is the molar mass of oxygen gas. Now I want to go through the charge. This section is available when a migration in electric field checkbox is selected in the transport mechanisms section of the interface. Enter the charge number ZW dimensionless but requires a plus or minus sign for each species. Now I want to go through the fluid sections. The fluid node is the main node used to model mass transfer in a fluid mixture with the transfer of concentrators. A species interface. The node adds the equations governing the mass fractions of all present species and provides inputs for the transfer mechanism and for the material properties of the fluid mixture. The settings in this node are dependent on the checkboxes selected under transport mechanisms in the setting window of the transport or concentrated species interface. The options available in this feature differs between capsule products. You can also visit capsule.com search product research specifications. Now I want to go through the model inputs, specify the temperature and pressure to be used in the physics interface. The temperature model input is used when calculating the density from the ideal gas law, but also when thermal diffusion is accounted for by supplying thermal diffusion coefficients. The pressure model input is used in the diffusional driving force in equation 3-6, that is when a Maxwell-Stefan diffusion model is used and when calculating the density from the ideal gas law. Now I want to go through the temperature. Select the source of the temperature field T. Select user defined to enter value or an expression for the temperature based on the unit Kelvin. This input is always available. If required, select the temperature defined by a heat transfer interface present in the model, if any. For example, select temperature HT to use temperature defined by the heat transfer in fluids interface with the HT name. Now I want to go through the absolute pressure. Select the source of the absolute pressure P. Select user defined to enter a value or an expression for the absolute pressure based on the unit postcode. This input is always available. In addition, select the pressure defined by a fluid flow interface present in the model, if any. For example, select absolute pressure single phase flow to use the pressure defined in a laminar flow interface with single phase flow as its name. Now I want to go through the density, define the density of the mixture and the molar masses of the participating species. The next chapter is mixture density. Select a way to define the density from the mixture density lays ideal gas or user defined for ideal gas. The density is computed from the ideal gas law in the manner of rho is equal to Pm divided by RGT. Here M is the mean molar mass of the mixture and RAG is the universal gas constant. The absolute pressure P and the temperature T used corresponds to the ones defined in the molar inputs section. For user-defined enter a value expression for the mixture density rho. Now I want to go to the convection section. Select source of the velocity field used. Select user defined to enter manually defines values or expressions for the velocity components. This input is always available. Select the velocity field defined by a fluid flow interface present in the model. if any. For example, select velocity field single phase fluid to use the velocity field defined by the fluid properties node fluid properties 1 in a single phase fluid laminar flow interface with single phase flow as the name. Now I want to go through the diffusion, specify the molar and thermal diffusivity of the person species based on the selected diffusion model. When using a Maxwell-Stefan diffusion model or a mixture average diffusion model, select a binary diffusion input type, table or matrix, and specify the Maxwell-Stefan diffusivities in the table or matrix. Then enter the thermal diffusion coefficients, the dAW to the power of T. When using a fixed law diffusion model, specify diffusion coefficient dWf and the thermal diffusion coefficient dAW to the power of T for each of the species. Now I want to go to the Maxwell diffusive matrix using a Maxwell-Stefan diffusion model or a mixture average diffusion model. The Maxwell-Stefan diffusivities matrix DI cup extended sign is a square meter per second can be specified by a table or matrix. For simulating involving Q species, the Maxwell-Stefan diffusivities matrix is a Q by Q symmetric matrix where the diagonal components are Y intervalues for the upper triangular components Dij, which describes the interdiffusion between species I and J. For the table input type, only upper triangular components Dij are listed. The name of the species pair consists of species in the first and second column. For the matrix input type, the numbering of the species corresponds to the order from top to the bottom used for all input fields for species properties. See, for example, the molar mass fields in the density section. The Maxwell-Stefan diffusivity matrix is used to compute the multi-component Fick diffusivities as described in multi-component diffusivities. Now I want to go through the diffusion coefficient. Using a fixed law diffusion model, the diffusion is by default assumed to be isotropic and governed by one diffusion coefficient, the W to the power of F based on the SI unit is a square meter per second for each species. To allow for a general representation, it is also possible to use diffusion matrices, diagonal symmetry, or anisotropic. Now I want to go through the thermal diffusion coefficient. To model thermal diffusion, prescribe the thermal diffusion coefficients di to the power of t based on the SI units kilogram per meter second by entering one thermal diffusion coefficient for each species in the corresponding field in a multi-component mixture. The sum of the thermal diffusion coefficients is zero. The default value for all thermal diffusion coefficients is zero. Specify the molecular and thermal diffusivities of the person species based on the selected diffusion model. Now I want to go to the migration in electric field. This section is available when the migration electric field checkbox is selected for the transfer of concentrated species interface. Now I want to go to the electric potential. You select user defined to enter a value or expression for the electric potential. This input is always available. If required, select an electric potential defined by the SDC interface that is present in the model. If any, for example, select electric potential easy to use the electric field defined by the current conservation node const and one in an electric constant interface easy. Settings for the mobilities are used for the mixture average and fixed law transfer models. By default, the mobility is set to be calculated based on the species diffusivities and the temperature using the Nernst-Einstein relation. To manually specify the mobility, select user defined for any mobility UML. See based on the SI unit is S molar per kilogram and enter one value for each species. The temperature, if you are using mobilities based on the Nernst-Einstein relation, is taken from the model input section. Now I want to go to the porous medium. Use this node to model the composition in a gas or liquid mixture as it is transported through the characteristics of solid porous medium. In addition to transport due to convection and diffusion, the node contains functionality to include species evolution through reactions in the fluid phase. Species transport in a porous medium is affected both by properties of the fluid phase as well as properties of the solid matrix. These properties are defined in the fluid porous medium node and the porous matrix node respectively. The porous medium node supports material properties using a porous material node described in the Capsule Multiphysics Reference Manual, where properties are defined per phase in a similar manner. Now I want to go through the bed inlet. This node specifies an input for the pore conditions in the solid catalyst pellet in a moving packed bed. Together with it, a bed outlet node should be also added. The solid pellet bed is rigid. The bed inlet and the bed outlet are usually set to opposite boundaries. Now I want to go through the boundary selection. Select boundary where the solid catalytic pellet bed moves into the reactor. These boundaries belong to the pellet domains which are defined in a porous material. Now I want to go through the inlet pellet concentrations. There are three ways to specify the pellet inlet conditions: from bed fluid conditions. The species mass fractions inside the catalytic pellet are the same as that in the fluid between pellet. From pellet initial values, the species mass fractions inside the catalytic pellet are the same as the initial values under the pellet node. User-defined, there are three different kinds of the concentrations input from the mixture specification list: mass fractions into the inlet mass fractions, and the mass fractions text field mole fractions into the inlet mole fractions. The mole fractions text field, the temperature and pressure will be taken from the fluid between pellets and at the boundary. The next one is molar concentrations into the inlet molar concentrations. CAPA is 0I, a percentage is molar per cubic meter in the molar concentration text field. The pressure will be taken from the fluid between the pellet at the boundary. Now I want to go through the surface species concentration table is available if there is any surface reaction inside the catalytic pellet and the inlet condition is set to from bed fluid conditions or user-defined. Enter the inlet surface concentration based on the assigned molar per square meter in the surface species table. The surface species concentration table is not available when the inlet conditions is set to from pellet initial values. In this case, the inlet surface concentrations are taken from the initial values node. Now I want to go to the transport properties pellets. Use this node to specify transport properties of a fluid mixture inside porous pellets. Now I want to go through the domain selection. The domain selection inherits all valid domains from its parent feature. For the invalid domain, no applicable is shown. Now I want to go through the fluid and matrix properties. Select the fluid density, ideal gas, or user define to enter an expression for the density rho of the fluid inside pellet. If a density variable is defined in the chemistry, we define variables for porous pellets selected in the pellet chemistry section, and the density can be selected from the list. Select dynamic viscosity, user defined for the fluid inside pellets. Enter a number or expression for the viscosity mixture if a viscosity variable is defined in the chemistry with the defined variables for porous pellets selected in the pellet chemistry section. The viscosity can be selected from this list. Select permeability from material or user defined for the fluid inside pellets. If user defined, selected enter a permeability expression for K. The default value is 1 multiplied by 10 to the power of minus 12 square meter. Now I want to go through the diffusion. To account for the effect of the porosity in the binary of diffusivities, select an effective diffusivity model, Millington and Crick model, Brugman model, Totiusity model, or no correction. Using one of the first three models, the effective transfer factor FAE is defined from the porosity and the fluid Totiusity factor in the manner of the FAE is equal to epsilon p divided by tau p. For no correction, the effective transfer factor is set to 1. For the Millington and Crick model, the effective transfer factor is tau p is equal to epsilon p to the power of minus 1 divided by 3. For the Brugman model, the effective transport factor is tau p is equal to epsilon p to the power of minus 1 divided by 2. For the tortuosity model, specify the tortuosity factor tau p. The specific diffusities are automatically adjusted for porous media transport using the effective transfer factor. Select binary diffusion input type table, the default, or matrix to input the binary diffusion coefficients table. In the Maxwell-Stefan diffusivities table, the first species 1 and the second species 2 columns are the species name for a binary diffusion coefficient. Select the diffusivities from the diffusivity column. If user-defined, select the interbinary diffusion coefficient expression in the diffusion coefficient square meter per second column. This column is editable with the user-defined selected, otherwise read-only. If there are diffusivity variables, define the chemistry interface which define variables for porous pellets selected in the pellet chemistry section. These diffusivities can be selected from the diffusivities column. Now I want to go through the matrix in the Maxwell-Stefan diffusivities matrix into the diffusivities expression in the upper part of the matrix. The default values are 1 multiplied by 10 to the power of minus 5 square meter per second into the thermal diffusion coefficient for different species under the thermal diffusion coefficient list. Now I want to go through the reactions pellets domain selection. The domain selection inherits all valid domains from its parent feature. For the invalid domains, not applicable is shown. Several reactions node can be used to account for different reaction mechanisms in different domains and pellet in the porous material. Now I want to go to the pellet. This section is invisible for default reactions node. It is visible for later added reaction routes. Select all or one of existing pellets for the non-default reactions nodes. Now I want to go to the reacting volume. Reaction text usually placed in the porous part fluid of the pellet can be, but can also in the whole volume of the pellet. When specifying reaction rate for a bulk species, the specified reaction rate has the basis for the pore volume or the total volume. With the pore volume selected, the reaction expression in kilogram per cubic meter second will be multiplied by pellet's porosity epsilon P. Now I want to go through the reaction rates. Select the reaction rate based on the SI unit is kilogram per cubic meter second. For bulk species I in the from RPEI list. Inter-reaction rate expression when user-defined is selected from the list. Alternatively, if reaction rate expressions have been defined in a chemistry interface with defined variables for porous pellets selected under the pellet chemistry section, they can be chosen from the list. Now I want to go through the surface reaction rates. The section is available when one or more surface species have been added in the surface species section of parent feature pellets. Specify the reactive specific surface area, total surface reaction area per cubic meter, SAPA reactant for all surface reactions. Under surface reaction rate for bulk species, specify rate expression RPA to the power of S based on the SI kilogram per square meter second for the surface reaction rate of each bulk species are participating in the surface reaction. Furthermore, specify any surface reaction rates for the surface species in the reaction rate for surface species table. If several pellet types have been defined, one set of surface reaction rates per pellet type can be set by selecting specific pellet under pellet selection. If surface reaction rate expressions have been defined in the chemistry interface with the defined variables for porous pellets selected under pellet chemistry section, they can be chosen from the list. Thank you so much for watching my tutorial video until the end. Today is the 14th day of May 2026. Time is 5:15 a.m.